So all that really needs to take place with conducting a two-tailed hypothesis test, again, is if you don't know the direction of where x bar may lie relative to your null hypothesized mu value ahead of time. Now, you never want to set these hypotheses after you've observed what's in your data, because that's really cheating. I mean, that can really screw up the laws of randomness and make us make conclusions that aren't really true in reality. So when we set up these endpoints, we just have to observe that whether the probability of the value that we have is either in this red tail over here or in this red tail over here, each of which has a probability of 0.025. So our conclusion in this case, now we could still say that, we conclude that the mean is significantly less, that mu is less than 15 based on our observed data, because it's directionally to the left. So since the probability of a sampled x bar being less than our observed x bar is 0, in other words, it's highly unlikely if the population mean is truly 15, so if in fact it's centered at 15 and you observe a 10.3 that has almost a 0 probability, 0% chance of happening, based on our cutoff probability of 0.025, if the population mean is truly 15, I have to read this again. Since the probability of a sampled x bar being less than our observed x bar is 0%, highly unlikely if the population mean is truly 15, based on our cutoff probability of 0.025. That is, since our p-value equals 0, which is less than alpha, we reject h0 at the 0.05 level. We conclude that tests have gone down significantly. So, again, I just reemphasize that you should never state your hypothesis after you analyze your sample. This is cheating and leads to results that violate the laws of randomness. The consequence is that the conclusions that are wrong. Now, sometimes you may get away with making right conclusions. Like you might say, well, what if the observed probability was actually 0.032? Well, you might say, well, if I just change my hypothesis to mu is less than 15, then I'd have 0.05 over in this tail, and 0.031 would fall in that tail. But 0.031 doesn't fall in this tail because it's actually somewhere out here. That's cheating. You're changing the results, and you're observing the laws of randomness before you try to make conclusions about laws of randomness. So we can easily make things up that aren't true. And that's to our advantage, because if you cheat with statistics, then you get data that's misleading and data that's ultimately wrong. So what are the advantages of this two-tailed test then, if it obviously makes our tail probability smaller? Well, we don't need to know where the sample mean will be relative to the null hypothesized mean. So we didn't know that x bar was going to be less than mu equals 15. We just wanted to see if it had changed. And we don't really care that it was a lot smaller then. We really just cared to see if it was different then. Similarly, there's a disadvantage, and the disadvantage is that alpha gets evenly divided between the two tails. And if it gets evenly divided between the two tails, it makes it more difficult to reject h0, because the likelihood of what you've observed or something more extreme has to be smaller than 0.025 if you're using alpha of 0.05. So the fact that each tail gets the same amount, but only your mean can only possibly fall into one of those, is the disadvantage. But again, if you don't know what to expect to begin with, you want to create a hypothesis stating that we don't know, and that's always the strongest way to go.